Good morning. I have quite a divergent line of thoughts going on in my head for the last couple of days, and nothing is getting finished. One of the main and major questions I had was to check this graph that I found on skepticalscience.org and see if I could actually get a numeric calculation of the heating effect of carbon dioxide gas. In order to do that, I need to know in particular what units the left-hand side of the graph was in. What units the vertical axis of the graph was in. The article from which the image came from is entitled Stratospheric Cooling and Tropospheric Warming by Bob Guercio. Bob Guercio has this graph here of the intensity in watts per meter squared per wave number. This is a histogram showing how much intensity there is due to each frequency of light. I have a similar graph that I've made here in Mathematica, and you can see that as I change the temperature, the amount of intensity at each frequency changes. It goes up to 134 degrees Celsius and goes down to minus 243 degrees Celsius here. So that would cover most of the range that happens on the surface of the Earth. Let's see what I can do to make my graph match the graph at Skeptical Science a little bit more closely. For one thing, theirs starts at 0, mine starts at 200. I think the problem was if I actually put 100 in as one of the as the input, it would fail. No, I was wrong. It works perfectly well with 0 being the low wave number. Okay, but now I want to fix this so that instead of going 0.05, 0.1, 0.15, 0.2, why does this have almost exactly the same thing except 2.05, 2.1, 2.15? That's a pretty large jump there. If I continued up 0.05, 0.1, 0.15, 0.2, 0.25, 0.3, there's no way the distance from here to here is 2.05. Okay, so here was my calculation of the Planck blackbody spectrum. It has to do with some strange and esoteric concepts. Number one, the volume of a sphere not in space, but in a place called the frequency domain. Together, the number of states available at a particular frequency times the probability of a given state being occupied at that frequency gives you a histogram of how many photons you have in each frequency at a given temperature. So I should say a temperature dependent histogram of how many photons you have in each frequency. However, if I had this analysis completely correct, then the units on this should not be watts per steradian per square meter per hertz, which is what this says right here. Rather, let's do a unit analysis of this beast to see what shows up. H is, over here, without units, 6.62 times 10 to the negative 34th, and that is in units of quantum action or angular momentum. You can write it as joule seconds. You can write it as kilogram meters squared per second. The frequency is in per seconds, so frequency cubed would be in seconds to the negative third. The speed of light is in meters per second, so c squared would be meters squared per second squared. H nu over k sub bt is unitless. I'll just write unitless. So multiplying these together, H gives you kilograms meters squared per second. Nu cubed gives you per second cubed, and c squared gives you meters per second squared. It's going to give us kilogram meters squared per second to the fourth divided by meters squared per second squared, which is kilograms, cross those off, per second squared. I don't find that particular unit helpful, so let's play with this a little bit. I said h was also in joule seconds, so let's try joule seconds here. Joule seconds per second cubed divided by meters per second squared, which is joules per second squared divided by meters squared per second squared, which comes out as joules per meter squared. Still don't like it because I wanted something in the form of watts per area squared, watts per meter squared, but let's compare it to what I said we would get, which was watts per steradian per meter squared per hertz. That actually, I think that looks promising. Watts is a joule per second. Meters squared is still there. And 1 over second. I just put 1 over second on the top, 1 over second on the top bottom, and I will have watts on the top per meter squared, hertz on the bottom. Now, what is the steradian? Well, if it's anything like the radian is a meter of arc length divided by a meter of radius. So if the radian and the steradian are similar, this comes out to be meters per meter, or unitless. So is a steradian, which is, I believe a steradian is equal to 1 over 4 pi times the celestial sphere. I don't know if I'm using that unit properly, but I don't know if there's a unit called the celestial sphere, but basically the idea is if I have the area of a sphere of 1, radius 1, then the area of that thing is going to be area equals 4 pi r squared, which would be 4 pi. So the whole surface area of a sphere, I don't know if I'm drawing that very well, but the whole surface area of that sphere is going to be 4 pi steradians. So the steradian would be what? The area of that. I think it has units of area over area, but I'm not sure. Area over area. I think it's in terms of this area divided by the surface of area of the entire sphere. I'm tempted to put this in, just kind of give some examples at first. Let's see. This quarter is pi steradians, and this quarter is pi steradians. If I divided it into 8, we'd have each quarter, don't know how to draw it, cut into 8s, but each quarter is pi over 2 steradians. There's some pieces chopped into 8 bits, little pockets. So each of those would be pi over 2 steradians. And then it says the radian is a meter of arc length over a meter of radius. So the steradian is a meter squared of solid angle per meter squared of radius, but I'm not really sure that second part makes sense. In any case, we have established that this equation here does give us yield units of watts per meter squared per hertz. If steradian is a unitless quantity representing units of area over area, we can also throw in per steradian. You'll see next I made two modifications to this equation. I changed the input and I changed the output. So instead of inputting the frequency into the equation, I am inputting the frequency associated with a given wave number. And the function relating those two is nu of k equals 100 times the speed of light times k. The idea is that we have 100 centimeters per meter times c is 3 times 10 to the 8th meters per second, and then our k is given in per centimeter. We can then cancel out centimeters with centimeters, and we can cancel out meters with meters, and we're left with per second. We're left with hertz. And I take that frequency, which is in hertz, and plug it right there into our original equation. But at the end of that, I don't want the output to be in watts per meter squared per hertz per steradian. I want it to be in watts per meter squared per centimeter per steradian. So I need to take that output and multiply that by 100 centimeters per meter times the speed of light, 3 times 10 to the 8th, 3 times 10 to the 8th meters per second. So then the seconds cancel out with the hertz, and we're left with, and the meters cancel out with the meters, and we're left with watts per meter squared per steradian per centimeter. Now the advantage of that is that now with per centimeter going this way and this being the units here being in per centimeter, I should be able to take the area under this curve and find what? Find watts per meter squared per steradian. The centimeter and the per centimeter is going to cancel out, leaving us with an area of I think this is intensity. No, that's incorrect. Luminous intensity is given in watts per steradian. This is a little bit more complicated. Watts per steradian per meter squared. Now, if I'm not mistaken, I already know the integral of what is under this graph. If I take the integral of b2 of k comma t from k equals 0 to infinity dk, I'm going to get sigma t to the 4th. So look at this, says 120 Kelvin. If I bring this up to 240 Kelvin, the area should be about 8 times as big, or 16 times as big. So bringing that up to 240, does that area look about 16 times as big as that area? More or less. If I cut that in half, it would be somewhere around there. Cutting in half again, it'd be somewhere around there and there. And Then I'll slice this into quarters. 1, 2, 3. Each of those areas is about a quarter of, or is about a 16th of the area, which I could believe is roughly about the same area as that there. Now that's not a very good proof, of course, but the other option is to do the integral of 1 over e to the, let's see, it would just be e to the t, or e to the 1 over t minus 1 with a few constants. dk, no, I don't want to put t in there. It would be e to the k minus 1 dk. And there would also be a k cubed term over here. That would be a kind of a simplification of the integral. So, though I am not good at doing, what do you call it, integration, I was hoping that Mathematica might be. I was expecting that if I integrated this formula from frequencies of 0 to infinity, I wasn't planning on infinity here, and use the temperature of 1 Kelvin, then it would make sense that we would get sigma times 1 to the 4th, which would be sigma being 5.67 times 10 to the negative 8th. And this comes out in the right order of magnitude. Instead of 5.67 times 10 to the negative 8th, it comes out to be 1.67 times 10 to the negative 8th. But I don't know how badly this affected it. It says that numerical integrate failed to converge to prescribed accuracy after 9 recursive bisections in the frequency near 1 times 10 to the 10th hertz. And integrate obtained this number, 1.67 times 10 to the negative 8th, and 8 times 10 to the negative 9th for the integral and error estimates. It says this integral can be, or it gives another example, and it says that this integral can be computed without difficulty using a larger number of recursive refinement. So let's try that. Use a higher number for max recursion. We still have the error with 12 recursions, but with 20 there is no error. It finds 1.8 times 10 to the negative 8th. Let's see if that temperature to the 4th holds. I'm going to plug a temperature of 2 Kelvin into the formula and see if we get 16 times our previous answer. And it does appear that yes, 16 times 1.8 times 10 to the negative 8th is 2.88 times 10 to the negative 7th. This is 2.88 times 10 to the negative 7th. So I'm going to end this video with a list of questions. Number 1, how do you really do the integration of the Planck spectrum over all frequencies and derive Stefan Boltzmann's law? I tried a couple of numerical integrations. With t equals 1 and 2, I was able to see the t to the 4th relationship, but I got a value of Stefan's constant of 1.8 times 10 to the negative 8th instead of 5.67 times 10 to the negative 8th. Number 2, in the article at Skeptical Science by Bob Guercio, Stratospheric Cooling and Tropospheric Warming Revisited, I saw the graph saying that the intensity in watts per meter squared per wave number started from 2.05, went to 2.1, 2.15, 2.2, whereas my own graph seems to be exactly 2 watts per square meter lower than that. Why is there this discrepancy? Question 3, and really this is a primary question that motivated starting this morning in the first place. Exactly how much warming should be expected based on this graph? we have a slight increase in the amount of infrared radiation absorbed by carbon dioxide when the concentration goes from 100 parts per million to 1,000 parts per million. Now really, in this instance, whether this represents 2.2 watts per meter squared or 0.2 watts per meter squared makes no difference, because what we're going to be comparing is this area under the curve, or between the two curves. The higher concentration of carbon dioxide appears to absorb just a slightly more frequencies of infrared radiation. Actually, there seems to be more to it than that. The blue graph seems to be emitting more total radiation in general. In some areas, the black line is above the blue line, and I've highlighted those right there. But in others, the blue line is above the black line. I would say that the blue line data is taken on a slightly warmer day than the black line data. So more heat is escaping at this wavelength and this wavelength, or sorry, let's make it red because that's how I drew this. More heat is escaping at these wavelengths simply because there's more heat is present. But there is also this region here where more heat is trapped by the carbon dioxide. Now I wonder if they had taken this data on a day where the temperature were exactly the same and the black lines and blue lines were perfectly aligned in all of the other areas, if these blue lines would be even lower in this region, hence increasing the area between the black and blue curves. But for now, it looks like this is what we have. This purple area here represents the predominant effect of the carbon dioxide-induced greenhouse effect on the atmosphere. This purple area here represents the predominant effect of carbon dioxide-induced greenhouse effect on our atmosphere. If we calculate the area between the two lines in that region, it will give us how many extra watts per square meter the carbon dioxide is capturing. Then we could use some form of Stefan Boltzmann's law to figure out exactly what the temperature difference is between the low carbon dioxide temperature and the high carbon dioxide temperature should be. Let's see if we can get an extremely rough estimate of how big this change is. This is about 200 wide. Say this is about a fifth of that. This is about a fifth of that. So the width of those areas is about 1/5 of 200, or 40 per centimeter. And then the height from here at 2.2 to there at 2.4 is about 0.2 watts per meter squared per centimeter. So 0.2 times 40, and there's two regions, so I'll multiply that by 2, is about 16 watts per meter squared. So I'm going to plug that in right here, equals 16 watts per meter squared. And then for the low temperature, I'm going to use 14.6 degrees Celsius. So 14.6 degrees Celsius is about 287.75 Kelvin. So here's the equation we want to solve for T. We have sigma is 5.67 times 10 to the negative 8th. We have T high, that's what we want to solve for. We have T low is 287.75, and we have 16 watts, which we just calculated. And so I'll take that 16, I'll take that 16, divide by 5.67 times 10 to the negative 8th, then add the 287.75 to the fourth power, and then take the fourth root of that, and I get 290.7, which is a change in temperature of 2.9 Celsius, or 5.22 degrees Fahrenheit. Now remember, the assumption there was that this was the only part that we had to take account of. I really think that if they had done this on the same temperature day, that maybe that other line would have been lower, and this actually would have been more than 16. Of course, that 16 was very highly estimated as well. So one final question to ask in a future video is fourth question is, other than experimentally, how can the width and depth of this carbon dioxide absorption region be determined? I think it is going to involve a frequency-dependent version of Beer-Lambert's law, as well as consideration of the location and temperature of the top layer of carbon dioxide in the atmosphere. But that will have to be in another video.